start.
Should I
So
go
Tony
ahead?
is going to
Okay,
tell
so
us about, yeah, proving that random CNF is unsatisfiable.
okay, great. Yeah, so just interrupt me whenever you have questions. I made slides because I'm going to give a more general talk about this, Simons, in a couple weeks. So yeah, especially if you have any comments, let me know either during or after. Yeah, so I want to talk about random instances of unsat formulas and how hard or why is it hard to prove them, even though they're in abundance. Okay, so first, just some basic background. So unsat, just define that to be the set of all unsatisfiable CNF formulas. And we're going to define a proof system, propositional proof system for unsat as it was defined by Cook and Reckhouse, so that it basically is general enough to include any NP algorithm. So the way they defined it is basically checks to see if something is a proof. So it's a polytime algorithm P that takes strings to unsat formulas, and you should think of P as taking an encoding of a proof in some standard proof system and then returning whatever it is that it's proving. And I'm going to in general use proof and like refutation and proof in the same way. So if I'm talking about an unsat formula, when I say proof or refutation, I mean refuting the unsat formula or proving it's unsat. And if it's a tautology, then when I say proof, I mean proving it's a tautology. So anyways, a proof system, you can just view it as a polynomial time procedure that takes as input a string, and the range of P is a set of all unsat formulas. That's completeness. Well, actually soundness and completeness. So we want the case that if F is in unsat, so the fact that it's onto is completeness. So if for any F that's unsat, there has to be a string Y or a proof such that P on Y outputs F. And since the range is just the unsat formulas, that's why it's sound. So you don't want to have proofs of things that aren't unsat. Does that make sense? So again, you can think of P as just a non-deterministic procedure that guesses the string Y and then verifies that it's whether or not it's a legal proof of. So given an unsat formula F, P, a non-deterministic procedure could guess the string Y and then check to see if it's a proof. Okay. And P is polynomially bounded if every unsat formula has a string Y or has a proof of length polynomial in the length of F. Okay. Is that good so far? I'll keep going if nobody says anything. Okay, so that's sort of a general definition of what a proof system is, and it incorporates pretty much every proof system that almost every proof system that we know of, all the standard textbook style proof systems, even proof systems that aren't specifically for propositional formulas. So you could take first order set theory, you could take piano arithmetic, any logical system that's strong enough to encode propositional formulas is, can be viewed as a propositional proof system in this sense. And since it's basically general enough to include all NP procedures, the way we defined it, NP equals co-NP if and only if there's a polynomially bounded proof system. Okay, does that make sense? So unsat is co-NP complete, and if there's a polynomially bounded proof system, then there's an NP procedure for a co-NP complete problem. Okay, and it's an easy if and only if. So proving that there's no proof system that's polynomially bounded is equivalent to showing that NP doesn't equal co-NP, or in other words, that there's no NP procedure for recognizing tautologies.
So it's a polynomially bounded proof system is a reduction, a polynomial time reduction from unsat to sat.
Yes. I think you're helping me, not asking, right? Okay, so I'm going to define a couple of proof systems as we go on, but the kind of more normal way that you would think of a proof is you think of having some fixed set of axiom or rule schemas, and a proof is typically a sequence of lines where each line is either an instance of an axiom or follows from two previous lines by one of the legal rules of the system, and where the final node at the bottom, the blue thing here is the thing you're trying to prove. So you think of a graph or a directed acyclic graph represents the implications, and the rules should be sound in the sense that if you can derive line L from L1 and L2, then it should be the case that anything that satisfies any assignment to the variables that satisfies L1 and satisfies L2 should also satisfy L. Okay.
So your lines are circles.
Yeah, and so the lines again, yeah, so you can think of the lines as being, yeah, some type of formula or circuit. Yeah. And depending on the proof system, the lines can get restricted, the depth of the proof, you know, the usual complexity parameters. So we'll restrict the types of lines, the number of lines, the height of the graph, blah, 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 okay, as we go on. Yes, I really like this quote. So this is general motivation for why you should care about proof complexity. And I thought it was quite funny, even though I'm not sure if Sasha intended this to be funny. But he says, everybody loves or ought to love proving theorems. If this appears exaggerated, let me remark that a theorem is perhaps way broader than it's commonly thought of. So this is one of the main points I wanted to make. Like originally you thought of a proof back like as in Euclid's book, a rigorous convincing argument. But what Sasha is saying is if you run any algorithm for say an NP complete problem, so for example, if you run a SAT solver on a formula tau and it tells you that tau is unsat, then the run of the algorithm on tau is a proof in the Cook-Reckhouse sense. And then he goes on to say this is true not just for SAT, but for all kinds of things. With a bit of oversimplification, one could say that the whole industry of software hardware verification is devoted to proving theorems of this sort, that a particular hardware or software meets its specifications. Also, approximation algorithms and integral gaps can be viewed as theorems, and so on. So one reason to be interested in proof complexity, even if you don't think it's going to lead to proving something about NP versus co-NP, is that it can actually help explain the complexity of specific types of algorithms. So you can study algorithms whose correctness proof is based on that proof system. And if you prove a lower bound for that proof system for some sequence of unsatisfiable formulas, then you're showing that in general, any algorithm that's based on that proof system is going to fail on some instances to run in polynomial time. So you'll rule out a large class of algorithms for solving NP hard problems or NP complete problems by proving proof complexity lower bounds for just the unsat regime. Does that make sense? If you've never seen this before, it might look weird, so I'm happy to spend a little more time on it, or I can move on.
Well, I don't know what other examples you'll give. I mean, if you gave, you'll have logical based and you know, I don't know, geometry based and algebra based systems, and people will see what you mean in classes of algorithms that are used to.
Yeah, if I forget to point them out, Avi, help me. But good, okay. So this is just saying the same kind of thing, that the transcript of a run of a SAT algorithm on an unset formula is a proof. And yeah, we'll see specific instantiations of this as we go on. So another thing that Sasha said in the same survey was the issue of, well, this has been an issue since I started the area, is really kind of perplexing that most people are pretty solidly convinced that NP doesn't equal co-NP, and therefore peddly little proof systems like bounded depth Frege, you know, or resolution, I'll tell you what those are in a minute. It should be clear then that those systems, you know, there's families of formulas that require exponential length proofs, but it's actually pretty hard to even come up with hard examples. So if you look at a standard textbook style proof system called like a Frege system, where the lines in the proof are polynomial sized formulas and the rules are just any set of sound and complete standard rules. I'll give you an example as time goes on. We not only do we strongly think most people that Frege systems are not polynomially bounded, but we don't really have a great, it's very different in the world of NP, where we have tons of things that we think are, tons of NP complete problems that we think are hard. And here in this case, we're really lacking in hard examples. And Sasha also brings up the point that we don't know of a single natural proof system where you can prove existentially that something's hard, but where it would not be witnessed by a specific hard tautology explicit in the good common sense. I can talk about that more in a bit, but so yeah, it's just pointing out it's awfully difficult to come up with candidate tautologies. We don't have tons of these NP complete or NP hard problems that people have been working on for hundreds of years. We have theorems, but the theorems either have proofs, and when they do have proofs, they tend to be, if the theorems are propositionally stated, the proofs, if we have them, tend to be polytime. I don't have many counterexamples to that. And otherwise, we have statements where we don't have proofs at all. And so we don't know if that's because they're not even unsatisfiable or whether it's because they are, but the proofs all have to be long. So we are in a unusual state that's quite different than trying to prove circuit balance for something in NP. This seems to be like even harder than that. Not clear that it really is, but this is the common wisdom.
So I'll stop here. I just wonder if the people that are in the audience who are analysts, for example, or doing something else, if this was too philosophical, or they want to ask Tony something.
Yeah, I'll get more concrete in a bit, but yeah, if something's not clear, or if you want me to go faster.
Yeah, I mean, I think basic summary is that if you are looking for a hard function that's hard to compute, you know which one to take. You take a random function.
Oh, I was going to get to this. I was going to say I have a slide on that, but go ahead. No, but you go for it.
Yeah, but if you are looking for something that's hard to prove, then we don't know what to pick. I mean, we just don't know. Something hard to prove for a general oppositional system. We have no idea what is hard.
Yeah. So there are some examples, and they tend to all be distributions of hard formulas. And I think the most common one and one of the most interesting ones is random formulas. So probably everybody knows what these are, but random distribution with parameters delta n and k is you pick uniformly at random delta n clauses. A clause is a disjunction of literals, where each clause has k literals in it, and there's n underlying variables. And as long as delta is sufficiently large, it's easy to show that, by a counting argument, that such a formula is unsatisfiable with extremely high probability. And we have this beautiful threshold result that there's, this is one of the many properties that has a sharp threshold behavior. So there's some particular, for every k, there's some particular value, delta star sub k. And for the case of k equals 3, the value is believed to be roughly 4.267, blah, 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 where when you pick n, the number of clauses, to be slightly less than that, the formula will be almost certainly satisfiable. And slightly more than that, the formula will almost certainly be unsatisfiable. And so lots of motivations for studying random formulas. Again, even forgetting about proof complexity, understanding when properties evolve through time in a nice distributional model kind of teaches us or helps us to understand structural properties that relate to our understanding of the properties we're interested in. And also, like Avi said, we have trouble getting hard examples. So this gives us a natural distribution of potential benchmark example for SAT algorithms. And what I'm going to be talking about today is, how hard is it to actually certify or prove that these random formulas are unsat above the threshold? And so I looked back at the survey that Paul and I wrote, and we asked this back in '98, I guess, how hard is it to prove lower bounds for random k-sat formulas? And it was known that at that time that we had strong lower bounds. Kvatal and Samaretti in a really beautiful paper proved lower bounds, resolution lower bounds for random formulas.
And can I ask a question? What?
Yeah.
Is there any I don't know, like do you going to consider let's call it randomized proofs at all, like things like
Yeah, so I when we talk about algorithms based on proofs, we usually mean complete algorithms, meaning that the algorithm should never fail, or it can be randomized, but it should never fail or out. I guess we could consider it. Well, I'm going to consider algorithms never say that a formula is unsat when it's not. Okay.
Yes, okay. Sure. There's probably also a reduction, right? Like at least in the case of SAT, you can probably build an assignment from such an algorithm.
But
you mean
you're
from
trying to prove that there is no assignment, or
yes, I'm saying that an algorithm that says that there is an assignment should also be able to find one. So it's easy to easy to certify that it wouldn't just say that there is an assignment.
Right, but there's a large class of algorithms like belief propagation and those types of algorithms where they just give up at some point, and so they look for an assignment, and if they don't find it, they give up, and then it's hard to know if they gave up because there wasn't an assignment or because it's unsat. So I'm not going to be talking about those kinds of algorithms today.
Okay,
that makes sense. So yeah, it's okay if the algorithm's randomized, but I really want it never to. Yeah, almost never to fail in the case where the formula is, it should never say it's unsat if it's sat. Okay.
Okay.
Yeah. The other kinds of algorithms are really interesting too, and we will talk about some of those because you can sometimes prove results about those types of algorithms as well using proof complexity balance, but it's harder.
Because they are like what you mentioned seems to be the more common kind, right? Like
well, it's more common it's definitely more common for refuting random CNFs. It's not so, they're not so good or common for more structured instances, but yeah, you're right. For random ones, like belief prop type of algorithms seem to work really well compared to complete ones. Is that what you mean?
Yes.
Yeah.
Okay.
Yeah, but they don't always provide proof. So
right.
They don't,
yeah.
I mean, for here, the whole point is giving a proof. You want to write, you don't need to give a proof, give an upper bound on the length of a proof.
Yeah, so the reason, the justification is that we already know that almost all these formulas are unsat. So, so we really want, we really want, if it is unsat, that it says so, at least most of the time. Anyways,
so I mean, maybe, Tony, most of the time it means several things. Almost all the formulas are unsatisfiable. Let's say 99%. You will be happy if it says unsat just for 90%, but for all of them, it has to provide proof that they are unsat.
Yeah, or I'm going to say it, and I'm going to say it slightly differently here. Okay. So a refutation algorithm is an algorithm that outputs yes. So it takes as input a random formula, and it outputs yes with probability at least a half, and it outputs no whenever the formula is satisfiable. So I always want it to say no if it's satisfiable, which is rare. And when it's unsat, which is most of the time, it should say unsat on almost all of those. So
the same thing.
Yeah. And Ficus' hypothesis, which he formulated in, I think, around 2002, states that for delta sufficiently large, in other words, as long as you pick the number of clauses above the threshold, but not too much above the threshold, so sufficiently large, but also sufficiently small, there's no polynomial time refutation algorithm. Okay. And a stronger version of his hypothesis, the non-deterministic version, states that there's no NP refutation algorithm. Okay, so that's the same as saying for delta sufficiently large, no proof system whatsoever can refute random unset formulas.
Now, this in particular implies that NP is different than co-NP.
Yeah, yeah. So like Avi said, the fact that you're proving that no proof system can refute a certain family of unsat formulas is exactly what you need to do to prove that NP doesn't equal co-NP. So this is a stronger version of that, because not only is it claiming that there is an infinite family of formulas hard for every proof system, or for every proof system there is a family that it can't do. This is saying specifically random unset are hard for every formula. And similar phenomena, this isn't just, I'm focusing on random unset, but similar phenomena hold with respect to other nice distributions and other nice threshold properties. So you can look at random KXOR, random KCSP, or you can look at graphs from the Erdos-Renyi model where you pick each edge with probability P to be in the graph. 1 minus p to not be in the graph, and you can look at various properties like when presence of a clique, say when p is a half, we know that there's a threshold behavior for cliques. Cliques of size log n will exist almost certainly when p is bigger than a half, and won't exist when p is less than a half. Likewise for other properties like containing a cycle or connectedness. So all of these properties have been studied in this context in very much the same way. I just wanted to point out nothing's unique here so much for SAT. So we don't know whether Ficus conjectures either one are true or not, but it's been extremely useful, the formulation of this conjecture, in the sense that it's been useful. I mean, if it's true, the conjecture is true, these results are interesting. Obviously, if it's false, then we're proving nothing. But we're unifying lots of different things. So approximating vertex cover, average case MCSP, pack learning DNF, all of these problems which defied hardness results, conditional hardness results before, now use under Ficus conjecture. We now know that all of these problems are hard. Hold on a second. Sorry. Okay. Okay, so why is it so hard to prove that a specific formula, random formula is unset? So one reason it could be hard to prove is because it's not true. It might be that these formulas are actually satisfiable. Sorry, I didn't mean that. Formulas are satisfiable, but it might be the case that it's easy to refute them. So what I mean is that it's not true is that it might be that a Frege system does have short refutations for formulas f above the threshold. The other case is that it doesn't, and we just can't prove that. And it's very hard to distinguish between these two things. And this is what Avi was saying before. A big reason that we can't prove lower bounds for proof systems for anything, not just for unset formulas, but in circuit complexity, the first thing you do is a sanity check, is you say, all right, well, let's just at least show that a random function is hard for the circuit class. And so you count all functions on n variables. There's like double exponential many such functions. And if you count all circuits of size, some polynomial in n, the number of such circuits, and therefore the number of functions computed by small circuits, is more like singly exponential in n. And so you get that almost all functions are hard. But for proof systems, the counting just doesn't work. So the number of proofs of size s, unfortunately, seems to be roughly proportional to the number of unset formulas. So this random model of random unset formulas, we know that they're almost all unset. We can't prove anything about the proof complexity. Any questions? Okay. So I'm not going to spend too much time. I'm not going to spend any time really talking about all these systems. Maybe some of you have seen this picture before, but people have characterized lots of the standard proof systems, and sort of at the higher up you go, the stronger the proof systems are. And when you have an arrow from one to another, it means that the top one is strict, can simulate the bottom one. So for example, Frege and extended Frege, the arrow from extended Frege to Frege means that any formula that has a Frege proof of a certain size S also has an extended Frege proof of size polynomial in S. So, the idea is to try to develop techniques to prove lower bounds for stronger and stronger proof systems. And, there's no end in sight. So I stopped at Zermelo-Frankel set theory and an algebraic system called IPS, but really we don't even know if there's an upper limit, if there's one proof system that can simulate all the other ones, or if there's just an infinite chain of stronger and stronger systems. And we do have exponential lower bounds for some weak proof systems, the ones below the green line. How you should think about this is the expressiveness of the lines. The difference between these proof systems is really just a matter of understanding what's the expressiveness of a single line in the proof. So for resolution, the lines are clauses, and that's all you're allowed to do is derive clauses from other clauses. So it's like a depth 1 proof system. AC0 Frege, the lines are bounded depth formulas, or bounded depth circuits of poly size. Frege, there's no restriction. Frege corresponds to like NC1, so the lines are poly-size formulas, or said differently, they're functions, Boolean functions that you can compute with circuits of log depth and poly size. And so as you go up, the complexity of the lines increases and our ability to prove lower bounds, diminishes quite quickly. And on the right side here are some algebraic proof systems. So because, there's lots of different NP complete problems, we don't have to stick with unset. We can look at, solvability of set of polynomial equations, or we could look at, proving that a graph doesn't have a clique. We could look at any NP complete problem and then come up with a proof system that's sort of hand-tailored to that co-NP complete problem. And the ones on the right are all sort of algebraic systems that are sort of most naturally used to prove that a system of polynomial equalities or inequalities are unsolvable over, say, 0, 1. Okay? And probably most of you have heard of SOS, which is a sum of squares, which has become a very popular proof system because of some nice properties that it has. It's quite related to semi-definite programs. And so understanding the proof complexity of SOS, proving lower bounds on SOS proofs, rules out a large class of semi-definite programming algorithms for solving NP-hard problems. So proof complexity of random set, for which of these systems can we prove that random formulas are hard? I mean, the line might look the same from the outside, but it is much harder to prove lower bounds for random distributions. So we'll see that we don't, for AC0 Frege, we do have strong lower bounds, but we don't know how to prove anything about random formulas. Cutting planes, that's what I'm going to spend a little time on in the second hour. We do have lower bounds, but only when K, the size of the, random K CNF, but K has to be order log n. And I'll tell you about that today. Questions? Okay, I just want to mention a bit about upper bounds because this is really quite interesting. So the question is, how much above the threshold do you actually have to be before it's easy to certify the random formula is unset? And here I'm looking at the case of K equals 3. So we're looking at random 3 set formulas. And we know that as long as you pick, more than 4.2 n clauses, it's going to be almost certainly unset. And the question is, how many more clauses do we need in order to not only, obviously, it'll get more and more unset, and eventually, if you have all n choose 3 clauses, then it'll be trivially unset because then you'll have all for any subset of 3 variables, you have all possible clauses on those 3 variables eventually, or eventually, if you pick enough clauses at random, you'll find a very local contradiction rate. You'll have for some set of 3 variables, all possible clauses on those 3 variables, so it'll be trivial to prove it when m is something like n to the 3rd. But the question is, so at some point it becomes super easy for almost every proof system. So the question is, for various proof systems, how big does m have to be? And when we started thinking about this, it seemed like this is ridiculous to me, but maybe it indicates that Fige's conjecture is correct. So for resolution, we know that if you pick roughly n squared many clauses, then you can certify that the formula is unset with small resolution proofs. And the reason is that once you have about n squared clauses, you can kind of like the implication graph of the clauses can sort of forms a cyclic contradiction that you can then find and then just go around the cycle to get the contradiction. And that was the best that we could do. So the best in any proof system. So that's a simple, for when m was like n squared, then resolution has small, resolution is a very weak system. So resolution has small proofs. And we didn't know how to certify, even if we took the strongest proof system that we knew of, we had no idea how to certify random set formulas when m for K equals 3 when m was less than that. And then this result by Fige, Kim, and Ofek and what showed that they proved non-explicitly an algorithm that could refute random unset formulas, the refutation algorithm, when m was n to the 1.4. And then Moeller and Ito Semret showed they actually formalized it in so-called TC0 Frege systems. So you can just think of that as Frege systems can refute random unset K CNF formulas as long as the number of clauses is at least n to the 1.4. So again, we're like way above the threshold, and that's the best that we have. And this result was not easy, the TC0 Frege one. Any questions? Okay. So I'm going to talk about lower bounds today. So what do we have for lower bounds? So I already showed you on that other slide the various lower bounds that we have for SOS, polycalculus, null sets resolution. So I'm going to explain, I'm going to give an idea behind the resolution lower bound and then about the cutting planes lower bound as well. And I'll just point out that all of these lower bounds, the number, so for the ones for resolution, the lower bound holds as long as the number of clauses is like into the 1.5. So it goes pretty high up. The other ones seem to break down closer to the threshold. So when K is 3, the lower bounds, as they're usually stated, are for the number of clauses being linear in N. And for cutting planes, we don't have any lower bounds for K equals 3. Again, I said this before, we have to have clauses of size order log n, and then m is forced to be polynomial in n in order for the formula to be unset. Any questions? Okay, so let me tell you a little about this, the exponential lower bounds for resolution. I'm not going to do the full proof, but I'm going to give you an idea, and I'm going to give you a way to think about resolution proofs that hopefully you'll like better than thinking of them as a rule-based system, which is a little bit hard to work with. First, I'll remind you what resolution is if you don't know. So resolution, like I said before, just deals with clauses, and so it's always refuting an unsat CNF formula, and there's no axioms, and there's one rule. So you start with all of the initial clauses of the formula F at the bottom here. So here we have 1, 2, 3, 4, 5 initial clauses of F. And the one rule is called the resolution rule, and what you can do with it is take two previously derived clauses, or they could be an initial clause or two previously derived clauses, and you resolve them. And what you do when you resolve them is you have to have a literal, see if I can get this thing to work. Oh, maybe I won't waste the time. So look at, so you have to have a literal that occurs in one of the clauses. Oh, here. So you have like, so you think of the clause as a set of literals. So C here is a set of literals. ORed with X is one clause. D ORed with X bar is another clause. So you can resolve on the variable X as long as it occurs positively in one and negatively in the other. You remove X and you take the disjunction of all the other literals without repeats. Okay, so that's the rule. And a refutation, you just like repeatedly apply the rule.
Yeah, Tony. Yeah, if people never saw it, the meaning of this is that if both of the clauses on the top were true, if you could satisfy both C or X and you could satisfy D or X bar with the same assignment, then the same assignment must be able to satisfy C or D. That's the rationale or the logic why this is a sound rule.
Yeah, and maybe it's easier to think about it is, you know, if X is false, so C or X is the same as if X is false, then C is true. And D or not X is the same thing. If X is true, then D. So this is like this is a very easy case of modus ponens. So it's saying if X is false, then C is true. If X is true, then D is true. And since X is either true or false, therefore we know that one of C or D has to be true. So that's my explanation for why the rule is sound. And it's also complete in the sense that if you have an unset CNF formula, you can always derive the empty clause by applying this rule, you know, the right number of times. So it's a sound and complete proof system. And again, a proof is just you can think of it as just a sequence of clauses where the initial clauses in the sequence are the clauses from the formula F that you're trying to refute. And every subsequent clause is derived from two previous ones by the resolution rule. And at the end, you want to derive the empty clause, okay? And the size of the proof is just the total number of clauses that occur. You can't really tell in this proof, but you can reuse the clause. It doesn't have to be tree-like, the proof. So in this example, the initial clauses were used more than once. This middle one was used more than once, and that's necessary sometimes. But other than that, in this particular proof, all the intermediate clauses were just used once. So this is considered a tree-like proof. A proof is called tree-like if the intermediate clauses are only used once. But in general, resolution proofs can be DAG-like. So in general, once you derive a clause like this one, I could use it any number of times to derive other things. And sometimes that can save on the size of the proof. Size being the total number of clauses. And the other measure that we have is the width of the proof. And the width is just, you look at the maximal size of any clause in the proof. Okay, so the width, and then the width of a formula is just the minimal width of a proof of that formula. Good. Okay, I'll keep going unless Avi slows me down again. Anyone else?
Yeah, okay. People will complain, hopefully, if they didn't understand.
Okay, so first of all, I just want to demystify resolution.
Maybe I can say, just repeating what you said, but a proof in the resolution proof system is just a sequence of clauses that each new one is derived from previous one by the simple rule, and which is just the widest or the clause with the largest number of literals in it. So a cheap, if this is a complexity measure, you want all of them to have few literals. That's one way to think about it. So it's a different measure than the size of proof.
Yeah, and maybe I'll point something else out that's useful. That if you know that something has a resolution refutation of width d, then you can always find it. You can find the refutation in time roughly n to the d, because you can just start generating clauses from the initial ones, and as long as the thing that you're deriving is of width at most d. So just repeatedly, and every time you're about to derive a new clause, just make sure you didn't already derive it. And so the procedure will run, there's only roughly n to the d many clauses of width d. So after that much time, you can't generate anything new. So you'll either have generated the empty clause or you won't have. So small width is good from the point of view of automating the system. If you have a small proof, you can find it relatively quickly. And it's exactly the same reason that if you have a small degree SOS proof or a small degree polynomial calculus proof, you can find it quickly. It's exactly the same kind of reason. So that's why we like small width. But for lower bounds, we want to show that the width has to be large. And it turns out that that's not just necessary, but that's sufficient. Okay, so I'm backing back up. So I want to spend a second about tree resolution, because tree resolution is particularly nice and easy to understand. You don't have to know anything about logic or proofs to understand tree resolution, because all tree resolution is a decision tree. So if you have an unsat formula F, we're going to be interested in the search problem associated with F. And that problem is the problem of given an assignment alpha to the underlying variables of F, output some clause that's falsified by that assignment. Okay. And it's a total search problem, because since F is unsat, on every assignment, at least one clause will be falsified. So it's a total search problem, it's in TFNP. And what I want to convince you of is that if you have a tree-like resolution proof, it basically is a decision tree for solving the search problem. And conversely, if you have a decision tree for the search problem for F, it can be viewed as a tree-like resolution proof. Okay, and the reason is just by picture here. So on the left, drawing the same resolution refutation that we had on the previous slide. And all I have to do here is relabel things to get the decision tree. So starting at the top, you look at which variable you resolved on. So at the very top, I resolved on x4. And so then what I do is I would query x4 at the root. And the left side, which is where we went to x4 negated, that's going to correspond to setting x4 to 0. And the right side is going to correspond to setting x4 to 1. And then I keep going the same way. So the way I label the vertices of the decision tree is I label them by the variable that was resolved on in the corresponding rule. Okay, and the clause associated with any node here of the tree, that sort of corresponds to the partial assignments that I've remembered so far. So x2 or x4 corresponds to remembering, did I get this backward? Yeah, I got my zeros and ones backwards, I believe.
No?
Yeah, sorry, I think these should be zeros down. I think these should be zeros. And the other way, the other way should be ones. The clause associated with any vertex, that should correspond to the assignment that x2 is 0 and x4 is 0. So in other words, when this clause x2 or x4 is set to 0, which happens exactly when you set x2 and x4 to 0, that's sort of what you're remembering at that point in time. So in the decision tree, when I label it the correct way here, this should be zeros, these are all ones. So, you know, I query x4, when it's 0, I go right. I query x2, when it's 0, go right. Query x3, 0, go right. Query x1. And then what you can see is that the bottom clauses of the formula F, they're all contained, they've all been forced, the clause labeling a leaf has been forced to false by the partial assignment to that, on the path to that leaf. Okay, so you can view then, so the label of the leaf is the clause, and that clause is falsified, which is what we wanted. So if you have a resolution tree like resolution refutation, you can sort of relabel the tree so that the under the relabeling, it's a decision tree for the search problem. And it's easy to go the other way too. If you have a decision tree, you can again relabel it by associating a clause with each internal vertex, which is just the stuff you've remembered so far, and then that'll correspond to a resolution, a tree-like resolution refutation. Okay, so for simple enough proof systems, understanding them is really, it's really all about understanding the complexity of total search problems. Okay, so we're looking here at decision trees for solving this particular type of total search problem associated with an unsat formula. Okay. Does this make sense? Because I'm gonna do the same thing in a little bit for the DAG-like case of resolution. So I want to make sure this is clear.
Any questions for Tony so far? But I find it really cool. Who invented it? This is Bas Pudlak game. Who invented this search problem?
Well, maybe you did, Avi. I think maybe you did in your paper with Newman.
I know. I wonder if it existed before. There's a very old paper with Lovas and Moni.
Yeah, I think maybe. I don't know if there's anything before you. I have to look around. Yeah. So I want to do the same thing for resolution now. So I want to see if we can view resolution as, in other words, is there an equivalence between a resolution refutation of F and some model, some model which solves the search problem associated with F. Okay, so then it would be natural to think that since tree resolution proofs correspond to decision trees for the search problem, you would think that maybe DAG-like resolution proofs would correspond to branching programs for solving the search problem instead of decision trees. So that's like the first try. Let me show you why why it's more subtle than that. So let's say you have F here is an unsat formula. So it consists of clauses C1 through CM, and think of F as a 3CNF formula. Okay. So what I want to show you is that any F that's unsat has a small branching program for solving the search problem. Okay, so that's not good because we know that not every unsat formula has a small resolution proof. So how do you, and this is the reason I want to show this to you is that as dumb as this example is, it's a huge stumbling block in proof complexity. And it's basically one of the reasons that we can't prove lower bounds. So what you do is you just query the variables of all the variables in C1, you query all of those. So I said, think of F as a 3CNF. So it's 3 variables that I'm querying. And, there'll be 8 different possibilities, and 7 out of those 8 times the clause will be set to true. And there'll be 1 unique assignment where the clause is set to false. So when the clause is, oh, sorry, I said it the wrong way. There'll be, did I say it the right way? I forget. There'll be 7 of them where it's set to true and 1 of them when it's set to false. So on the 7 of them, when it's, what did I do wrong here? Yeah, I think I got the pictures. Yeah, I did the picture backward. So it should be like, so there should be, oh geez. So it should be, let me draw this. So there should be one assignment where the clause is set to false. So C1 equals C1 restricted by this assignment is false. So that's this one. And then we label this, we're done, and we label this leaf with clause 1. Okay. And all of the other assignments, the clause C1 has been set to true. So for all of those assignments, all 7 of those, we have to continue. And then what we'll do next is query the variables of C2. So I just got these things in the wrong way. Does that make sense? There'll be one where C2 is set to false, and all the other ones, C2 is set to true. And so we'll keep going in that way.
So it's an algorithm that just tries to...
It's the dumbest possible algorithm. It's just because you know ahead of time that the formula is unsat, you know that one of the clauses is going to be made false. So I just try the first clause. The only thing I have to remember at every point in time is that, so far I didn't find, of the first I clauses, they've all been satisfied so far. And I don't have to remember anything about the assignment to the variables. And at the very end, when I get to the second to last clause, if that clause was set to false, then, I'm done. I label it with clause number n-1. And otherwise, I have no proof of this, but otherwise I just say, okay, so then it has to be that the last clause was set to false. And notice that the paths to this one here, they don't falsify the last clause CM. So it's the transcript of this branching program doesn't give you anything like a proof, right? It doesn't convince you. It shouldn't convince you that this formula F is unsat.
Tony, since it's a branching program, even though there's this like factor 7 or something at each level, it doesn't blow up in size?
Yeah, because I'm moving all of these to, so in other words, this is what the top one looks like. If C1 is like X1 or X2 or X3, then here I query like X1. And when X1 is 0, I go this way. And when X1 is 1, I go this way. So
right.
That's what I was trying to draw. And here you label this with clause 1 has been falsified, and otherwise you basically forget everything that you queried, because you can requery X1, X2, X3 any number of times. So the length of the branching program will be, linear in M, the number of clauses, be real small, long and skinny. But the reason this is unsatisfying is, well, first of all, there's no way it's going to correspond to a resolution refutation, and doesn't correspond to any refutation, because like I said, when you take any of these paths that lead you to this last one here, you have no certificate or proof that nothing. You just know that because none of the n- first ahead of you were unsat, it must be that this one is.
Makes sense. Thanks.
Yeah. So yeah,
in general, in branching programs, you expect that computational path will be consistent with the assignment, but in the path of this program, you might follow an edge labeled X5 and then continue on an edge labeled X5 bar, right? So it would not be a legal path, but in this program, it is allowed. So that's why it doesn't work.
Yeah, it's not the only reason, but yeah.
Yeah, that's not the only reason.
Yeah, good. So the second try is to fix this up in a way that's going to make sure that when you reach a leaf, not only is it labeled with a clause that's been falsified, but you have a certificate of it. So what would a certificate be in this case? Well, it would be it should be the case that any partial assignment that makes it to that leaf. So if you follow any path to that leaf and you look at all of the kind of remembered, so if you look at all of the remembered, the partial assignments it's remembered. In other words, at any particular node, you can look at all the assignments that make it to that leaf. And if you queried a variable on one path and you didn't query it on another path, then you couldn't have remembered the value of that variable. Or if you queried it on two different paths and they have different values, you couldn't have remembered it. So the remembered ones are the ones where on every single path to that node, you've queried the variable and it's taken on the same value. So you kind of have a certificate that this clause really is falsified if the set of remembered variable or literals falsifies that clause. Okay.
So in particular, you are already labeling the nodes with clauses.
Yes. Yeah. So the second try here is we're going to have a DAG, but it's going to have more conditions on it than just an arbitrary branching program. So we're going to think, again, we're going to think of every vertex as being associated with sort of a partial assignment, which is like what you remember, just like in a normal branching program, it's the stuff you've remembered and remembered the way I just said. And at the root, it's the function is that the all one function, all assignments start at the top. So you haven't remembered any, you haven't queried anything. So all possible assignments start there, and you're sort of tracking these sets associated with the vertices are, subsets of all assignments, and they're tracking which assignments make it to that vertex. Okay. And the second property is the soundness property. So it's saying that, so let's say this is V, and this is U, and this is U prime. Down here are the clauses of F. Okay. And so the leaves, so the set CL associated with one of these are, the partial all assignment. So if clause, let's say CL is the clause X1 or X2 or X3. So I'm reusing the name CL to mean two different things. So I'm sorry about that. So if this is the clause associated with this leaf here, then the partial assignment is, or the set of assignments that we're interested in is a subset of all the assignments where X1 is false, X2 is false, and X3 is false. Okay. So this second condition here is the soundness condition, and it's saying that this set of assignments has to be contained in the union of these two sets. So said differently, if you falsify, if you think about labeling each of these nodes with a clause, so if you think of these C sub R's as being clauses, then you're saying like if you've any assignment that falsifies U, the clause associated with U, and falsifies the clause associated with U prime, must falsify the clause associated with V. Okay. So I don't know if you like to think of it in terms of clauses or in terms of a family of, a subset of assignments. If you like to think of it as clauses, then the associated set of assignments is you negate the clause, and it's all the assignments consistent with that. Does that make sense to everybody? Maybe if I do an example, it'll help. Let's do an example. So here's an example here of an unsat formula F with 4 clauses in it. And this is just a resolution refutation of it. And the reason this is a legal proof is we can sort of associate. So again, we associate the top here with all possible assignments, 0, 1 to the 3. Okay. And here this corresponds to querying the variable x3, and on the left side we're setting x3 to 0, so that this corresponds to the set where x3 is 0, and the other variables are x2 equals x1 equals star. So it's all assignments consistent with x3 being set to 0, and on this side it's all the assignments corresponding to setting x3 equals to 1. Okay, and again here now, when we resolve on x1, going this way, we set x1 to 0, and here we set x1 to 1. So here the associated set is when you set x1 equals to x3 equals to 0, and x2 equals anything. Does that make sense? So you have these sets of assignments associated with every vertex, and this DAG has the property, this soundness property. So the set associated with each vertex has to be a subset of the union of the sets associated with the children. And then you have to have at the leaf that the set associated with the leaf is basically corresponds to the clause that you labeled the leaf with. So it is a branching program, but it has this extra property. The most important thing to know is this extra property that all of the paths that make it to a leaf, if you look at their what's remembered, in other words, all of the variables that have been queried on every path and set in the same way, all the remembered variables, they have to force this clause to false. Okay, so in other words, you actually know, based on the partial assignment to the node, based on what you remembered, you actually know that that clause is false. You have a certificate of it. Does that make sense? I'll keep going, but if I'm happy to. Okay, no questions? Okay. Okay, so I'm just going to quickly tell you a little about the resolution bound, and we'll take a break, and then we'll talk about the cutting planes. So to prove the resolution bound, it's a two-step thing, like I kind of alluded to before. The main step is to show that for any formula F, random formula, that any resolution refutation of it has to have linear width. So somewhere in the refutation, no matter how big it is, you have to have a clause of linear width. And once you have that, thanks to this general result due to Ben Sassoon and Avi, they have a general result that states that anytime that you can always go from a width bound to a size bound. So they prove our upper bounds that if you have a small size S resolution refutation, then you can convert it to a refutation of width relatively small, square root of n log S. Okay, so in other words, if you can prove a linear width bound, then that's going to tell you that S, the size, has to be, exponential, like 2 to the n to the epsilon, as long as and again, I'm doing all this for the case of K constant. Okay, so all you have to do, based on their great result, all we have to do is prove a width bound. And the width bound is very easy for random formulas. It follows from expansion properties of formulas, or spreadness of the formula. So basically the idea is that if you look at the clause variable graph associated with the formula, so here's all your C1, C2, Cm. These are your random clauses, and these are your variables x1 up to xn. And each of these has degree 3. And I'm not even paying attention to the orientation of the literal. So I connect C1 to the 3 variables that are in the clause, whether they're negated or not. Now, this bipartite graph is almost certainly, when you pick these clauses C at random, this will have high expansion, in the sense that if I pick any subset of these vertices on the left of size, say less than, I don't know, n over 2, the set of vertices on the right will be, some linear in n. And moreover, I can show that it has big boundary expansion, meaning that there'll be a lot of variables on the right that occur in exactly one clause in the set on the left. So if this variable here, x5, just occurs in this one clause here and doesn't occur in any of the other clauses in here, then this is a boundary variable. And expansion of random formulas tells you that this graph has high expansion and high boundary expansion. And so therefore, you can take any refutation, find the first clause in the proof that was derived from, I don't know, n over 2 initial clauses. And you know that there has to be one, because any subset of n over 2 initial clauses is going to be satisfiable with very high probability. So that means that there has to be some clause that came from at least n over 2, or let's say n over 4 initial clauses. And since we find the first one, we can argue that, well, it has to have been derived from somewhere between like n over 3 and 2n over 3 initial clauses. Okay, and so that gives us a subset of clauses over here that it was used to derive it. And by boundary expansion of this bipartite graph, that means that there's a lot of variables, a linear number of variables that occur exactly once as we look over all of these clauses. And if the variable occurs just once and it was used, then it couldn't have been removed. It has to be sitting there for the ride, because you couldn't have resolved it. If you just used these clauses to derive your special clause C star, and you had some variable in one of those clauses and it never occurs anywhere else in any of the other ones, then it's just gonna, it has to persist. It has to still be in C star. Okay, so just simple application of boundary expansion gives you that any resolution refutation of an unsatisfiable formula has to have big width. Does that make sense? Okay, so I just want to say one quick thing, and then we'll talk about the more complicated cutting plane style result. So so this means that we don't just have, we can study not just threshold behavior of the property of being unsat, we can actually look at like a different threshold, which is for a proof system where its threshold lies. And what I mean is like for what value of m can it refute, you know, for some value of m or delta up here, eventually resolution, this green line will come down. In other words, it should eventually become easy for resolution to refute random formula if the number of clauses is big enough. And the question is, where does that happen? And again, for resolution, we know it's way off to the right, somewhere between like n to the 1.5 and n squared. And for other proof systems, yeah, we really have no idea. So it's a really interesting picture that we have here where the dotted blue shows the threshold behavior of unsat formulas, that they're almost certainly unsat above 4.267 n many clauses. Below that, almost certainly satisfiable. But resolution thinks that even when you're way above the threshold, resolution still thinks that the formula is satisfiable. So passing this transition point, this critical point, delta 3 star, is completely like unnoticed by resolution. Resolution just like super optimistic and unfazed and thinks the formula is still satisfiable. And again, we think this is true for all proof systems. So, and then one last little thing. So, okay, so you might say, well, who cares? But it turns out that you can understand and prove lower bounds on classes of, like I was saying in the beginning, you can study various classes of algorithms for solving SAT, and a huge important class of algorithms are based on resolution. They're clause learning, the procedures where you basically start by running you use various heuristics, which I'm not going to tell you about, but various heuristics in order to build a decision tree for solving the search problem. But you also use memoization to remember things that you've learned along the way. So it ends up being what you end up with the transcript when you run it on an unsat formula is you'll end up with a resolution refutation. And when you run it on a SAT formula, it'll eventually find a satisfying assignment. But by proving strong enough resolution lower bounds, you actually can show that a large class of algorithms based on resolution will require exponential time even on SAT instances. And the way that this was proven by Dimitri Apolakis, Paul Beam, and Mike Malloy. And the idea is they took random unsat formulas, and then they looked at typical procedures for building this DPLL, or this decision tree. And for the typical procedures, what happens is eventually, so you're querying a variable, you're setting that variable to say 0 or 1, and then you think about restricting the underlying unsat formula by that assignment. So you have the C in a formula F, maybe you query X3 here, and here you set X3 equals to 1, say on this side. And so that, then the underlying formula is F restricted by X3 equals 1. So now at this vertex, that's what you're trying to refute, or you're trying to find, solve the search problem for that restricted formula. That's called the residual formula. And what happens is, as you set more and more variables, the residual formula will be some mix of 2 and 3 clauses. And this is, sorry, I meant to tell you that I'm running this on a SAT. I'm actually running this on a formula F that's satisfiable. So think of F as being a satisfiable instance. So where I'm picking delta to be below this threshold. So think of F as being a random formula, but now delta is below the threshold, so it's satisfiable. And we're looking again at common heuristics for solving SAT, common resolution-based heuristics. And again, what happens is you start querying variables that lead you to a residual formula, which it starts off being all the clauses have size 3, but eventually it'll have a mix of 2 and 3 clauses. And what they show is that for this large class of heuristics, that even though the formula is satisfiable, what'll happen with overwhelmingly high probability is that the search algorithm will get stuck in the sense that it'll come across an unsat residual formula, will be a mix of 2 and 3 clauses. It'll be unsat, even though if you follow this purple path, you get to the satisfying assignment. But before you know to do that, you're stuck with refuting this unsat formula F prime that still has expansion properties. So you can show that any resolution refutation of F prime has to have exponential size. So you're going to be stuck here refuting this F prime, which will take you exponential time. And it's not until you deal with that that you're going to back up and find the purple path. So again, by proving lower bounds for slightly more complicated distribution of unsat formulas with mixed 2 and 3 clauses, they're able to show that the large class of algorithms, even when they're run on satisfiable formulas, will require exponential length proofs. Okay, so do you want to take a break, 5-minute break? Is that good?
Yeah, that sounds good. Yeah.
Okay,
let's
great.
take a 5-minute break.
Okay.
All right. Let's continue with the talk.
Okay, great. Yeah, so the next thing, everybody back or hear me? Can you hear me, right? Okay, good. So the next result I want to tell you about is a result from a couple of years ago with Noah Fleming, Dennis Pankratoff, and Robert Robert, and also proven at the same independently by Pavel Hrubish and Pavel Pudlak. So this is going to be a similar lower bound for cutting planes refutations of random K, C, and F. But like I said, K has to be at least order log n so far for our proof to work. We think the result's still true for K constant, but yeah, that's one of the reasons I wanted to talk about this, to maybe get some interest in people from other areas or combinatorics working on it. But I think it's quite closely connected to proving stronger sunflower lemmas, which again is closely connected to better lifting results, also closely connected to improving this result for quantitatively for smaller K. Do people know what cutting planes is?
Right.
I'm going to tell you, even if you don't.
Cannot
I'm just curious. Yeah, I'm not going to assume it, but I'm just curious.
I expect some people in the audience don't.
Okay. So for a cutting planes refutation, the lines are not, they're actually linear inequalities. So you still have Boolean variables xi. They're not, anyways, you have variables xi and you have an axiom that says that xi is between 0 and 1. So you have the axioms that say xi is less than or equal to 1, less than or equal to 0. And lines are linear inequalities. So these AIs and B are weights, and they're integer weights. And I'll show you the rules on the next page, but these are the only axioms. And you start with some initial set of linear inequalities. And again, if they're unsolvable, then you want to, if they're unsolvable over 0, 1, then you want to derive, you're trying to derive the inequality 1 is less than or equal, 1 is less than or equal to 0. Okay. And we can assume that the magnitude of the weights, the length of, that the length of the weights in binary is a polynomial in n. So the magnitude is, at most, I think it's actually something like n factorial. But anyways, so again, so you can measure a cutting planes proof is going to be a sequence of lines where each line is a linear inequality. And we can measure the size by the total number of lines because the weights are never going to grow too big. So the size is measured by the number of lines is going to be polynomially related to bit size of the whole proof. And then when I put, so CP denotes cutting plane system. So that's just going to be a particular sound and complete proof system where the lines are linear inequalities. By particular, I mean there's a specific set of rules for it. CP star is going to be the same system, but now where I'm going to force the weights to have length polylog n instead of polynomial in n. And there's also something called semantic cutting planes where you don't even care what the rules are at all. You just you're allowed to derive any inequality from 2 previous ones as long as it's sound. So in other words, as long as any assignment that satisfies the upper 2 inequalities also satisfies the bottom inequality, then you can derive it. Okay, so that's a semantic system where you don't even have any specific rules. And so with the result that we have is a lower bound for general cutting planes, but today I'm going to mostly focus on the case of the small weights. It's not too big of a deal, but just to keep probably won't even get that far. So for the cutting planes rules are pretty natural. So you're allowed to take two inequalities and add them up. You can multiply any inequality by a positive integer on the left and the right. And you can also divide by a positive integer. And so here, if you have weights where some positive integer c divides all the weights on the left, then I can divide by c. And the beauty of this is on the right-hand side, I can round up, even if b here doesn't divide c. So this is the interesting rule because it's this rule is the one that's knocking out non-integral solutions. Okay, so this is where you're getting your power. So you're trying to, you're trying to derive this false inequality that 0 is bigger than 1. And so at some point you're going to have to, because there are legal solutions that are non-integral, you're going to have to, there has to be some rule that's going to be cutting out some of those non-integral solutions. And this is the one.
Maybe, I don't know if you said, but that's it's a way of proving that some polytope does not have integer points in it, right? So that's the nature of the system.
Yeah, so I sort of said this proof system came from the Kvatal-Gomery branch. There's different names for it, but different procedures that are used in the optimization world. Again, where you, just what Avi said, you have a polytope and you're trying to optimize something over the set of all integral points in the polytope, or in my case, integral points that are either 0 or 1. And so this rule allows you to, you start with some polytope, and let's pretend that the polytope came from an unsatisfiable CNF. So the inequalities are just clauses converted. So then we know that the polytope, it's not empty, but it doesn't have any 0, 1 points in it. And so the rules allow you to kind of, in that case, start with this polytope that's not empty, but has no 0, 1 points in it, and applying these rules repeatedly, eventually get down to the empty polytope. Okay, that's what you're trying to do in cutting planes. And again, this is one proof system. There's other ones that have, so all of the semi-algebraic ones, SOS, Straley-Adams, those are similar systems in that they start with polynomial inequalities, slightly more general than this. And again, you have some polytope defined by those, and you're trying to, in the case where you start with something that's unsolvable, that has no integral solutions, you're trying to apply the rules of the system in order to get to the empty polytope. Okay, but again, you can think of it more generally for solving approximation problems, where there you're trying to, maximize or minimize some objective function subject to a bunch of constraints. And this is, and you're, you really care about the integral, the maximization over all the integral points. But since you relaxed it, the integrality gap will tell you sort of how, give you some indication of how far away the procedure is to whatever. I don't know how to say this in a clear way. The integrality gap is like the difference between the best non-integral solution that it finds in its whittled down polytope and the best integral solution. So if that gap's really big, then an algorithm based on the proof system is not going to do very well in terms of finding a good approximation to whatever the optimization problem is. And if the integrality gap is small, that's an indication that the proof system, with appropriate rounding, might be able to come up with a good approximation algorithm. Okay. But I'm just going to be thinking of this of cutting planes as a refutation system for unsat formulas. Okay. So everybody,
I don't know if you said this, but it's easy to encode clauses.
Yeah. So if I have like x1 or x2 bar or x3, I'll convert this to x1 plus 1 minus x2 plus x3 is bigger than or equal to 1. I think I did it right. And this conversion has the property, that if there's a 0-1 assignment that satisfies the clause, if and only if that assignment satisfies the inequality. So I can just convert all of the clauses to inequalities, and if the formula that we start with is unsat, then these inequalities will not have any 0-1 solutions. And so we're trying to now derive a cutting planes refutation from these inequalities, plus the ones that say that the variables are between 1 and 0. Okay?
Yeah, and another comment is that this is a stronger system than resolution. So
yeah,
it can...
great. Yeah, so this can easily simulate resolution. I'll let you do that for yourself, but it's stronger than resolution. And it's been kind of difficult to prove lower bounds for cutting planes, even though in the circuit world we think we understand linear inequalities pretty well, but proving lower bounds for the corresponding non-deterministic version, which is like cutting planes, it took some time, and we still don't really understand cutting planes as well as we would like to. So I'm going to tell you first about the high level of how lower bounds were proven for cutting planes initially for other structured families of formulas, and why that technique doesn't work directly for proving lower bounds for random CNF, and then how to prove it for random CNF. It's still inspired by the original methods. So the original methods all kind of involved basically finding the right structured set of unsatisfiable formulas. By right, I mean ones where you could associate the search problem associated with that unsat formula somehow with a hard monotone function, in the sense that if you had a short refutation of this structured family of formulas, you would somehow be able to extract from the refutation some algorithm, monotone type of algorithm for solving this related monotone function. And then, so basically it's a reduction to a monotone circuit bound. Okay. And the way this is done in the past is again, F is now not a random CNF, it's a highly structured one that I'm going to pick, but you basically partition the variables of F into two parts, X and Y. And the reason that we're doing that is we want to think of the lines, which are inequalities, we want to think of them more generally as functions that are easy to compute with a low communication protocol, okay, under any partition of the variables. So if I partition all the variables into two groups, call them X and Y, and one player has X and one player has Y, if the weights of the linear inequalities aren't too big, then the players can send, send just a couple of bits back and forth, a few bits back and forth in order to be able to compute the value of the linear inequality. Okay, so we're going to abstract away, instead of just thinking about cutting planes, we're going to really be thinking about any proof system where the lines in the proof can be computed or can be evaluated by a low communication protocol under any partition of the variables. Okay, so again, the variables, it's going to be important to us that the variables of the function are partitioned into two sets, and then we're going to make this transformation from the search problem associated with F on a particular input assignment to X and Y. We're going to somehow find a way to morph that to an associated set. We're going to think of the assignments to the X variables, each assignment to the X variables, as a one input to an associated monotone function. And likewise, the assignments to the Y variables, we're going to be able to view them as zero inputs to an associated monotone function. And then we're going to be able to show, assuming that F is of nice form, that, that if we have a small refutation of F, cutting planes refutation, then this corresponding monotone function, it's going to be hard for a monotone model of computation to say yes on all the one inputs X and zero on all the Y inputs.
Yeah, so again, for those who don't know, I mean, the complexity theory knows how to prove circuit law bounds if the circuit is monotone. So that we are trying, I guess this whole approach is trying to use something we know in a context that's very different in order to prove complexity law bounds in cutting plane.
Yeah, and I'll just say one more thing because you set me up so nicely. So we would be happy in general for the stronger proof systems, we would be happy if we could just do this reduction to some function that we think is hard in any model of computation. Even a conditional result would be great. So I just want to point out that it's true that in this case, we're able to reduce it to the hardness of a function in a model of computation that we have lower bounds for, namely monotone circuit model. But for stronger proof systems, we would love be able to do a similar thing, even if we just got to some function that's hard for polysize circuits. We don't even know, like we don't even know how to prove conditional results of that type for, say, Frege systems.
Yeah, let's say P is different than NP.
Yeah.
Or something. Yeah.
Yeah, so there's two examples of this in the previous work. One is the method of interpolation. So the difference between these is how you concoct the original formula F so that you can reduce it to a monotone circuit bound. In the original, the first lower bounds for cutting planes, this was done by so-called feasible interpolation. So an interpolant formula is of a very special type. It's a formula of the type like A, X, Z, and B, Y, Z. So this is a CNF formula. This is a CNF and this is a CNF. And they have these shared variables Z, and A has private variables X and B has private variables Y, okay? And this is called an interpolant type statement. The reason why is that if the whole thing is unsatisfiable and you pick an assignment, say gamma, an assignment to the Z variables, and you plug that in, if you plug that into this formula, okay, then you'll be left with disjoint formulas A of X and B of Y, right? Because the Z will be gone. And if the whole thing's unsatisfiable and it's now the conjunction of two disjoint formulas, then you know that one of the two, at least one of the two subformulas has to be unsatisfiable, okay? And if a proof system has feasible interpolation, if any time it can refute a statement of this interpolant type, you can extract from the proof a small circuit or sometimes monotone circuit that computes. So the interpolant, so you have an algorithm, let me call it algorithm or circuit. Let's call it C, that takes as input this assignment gamma, and it outputs either 0 or 1, and let's say it outputs 1. So if it outputs 1, then basically C tells you which of the two is unsat. So C of alpha will say 1, 1. So interpolant for this unsat formula A and B is a function that takes as input an assignment to the shared variables and returns, it's a search problem, but it returns, which of the two is unsat. If they're both unsat, then it can give either answers. So that's why it's a search problem and not a function. There's many different functions that solve the search problem. But if the proof system has this nice feasible interpolation property, it means that let's say cutting planes does have this property. So what that means is that if cutting planes, for any formula of this type, if cutting planes has a refutation of it, then I can extract from the refutation a small circuit C that solves this interpolant problem, okay? And under certain conditions on A, basically if A is monotone in X, then not only can it solve this problem, not only can you extract a circuit for this, but you can extract a monotone circuit that solves the search problem. Okay, so that's the sense in which when you use feasible interpolation to prove the lower bound for cutting planes, that's the sense in which you take, you convert the question, or you reduce the question of proving lower bounds for cutting planes to a monotone circuit bound. So this involves, first of all, showing that cutting planes can refute this formula. So you have to come up with a family of formulas of this type where cutting planes has small refutations of the formula. But on the other hand, where if cutting planes had small refutations of the formula, then you would have a small monotone circuit for solving this interpolant property. And then we would like to use known lower bounds for some monotone function, monotone circuits for solving some function to then figure out a way to, to go backwards and figure out a way how to come up with this interpolant statement. So the obvious thing to do, because the lower bounds that we have were originally due to Rasbroff, that separated graphs with cliques of size k from graphs with colorings of size k-1. So the best thing to do is to work backwards from that. And so the interpolant statement that's used here is called the clique-co-clique statement. And basically you think of Z as being a graph, that's encoding of a graph, and you think of X as being encoding of a clique of size K in the graph, and Y is an encoding of a K-1 coloring. And the formula states that the graph G, the clique part says that the graph Z contains the clique described by X, and the color part says that the graph Z contains the co-clique as described by Y. Okay, and that's unsatisfiable. And by feasible interpolation, if you had a small cutting planes refutation of it, you would be able to extract a monotone circuit that would be able to say yes on all cliques of size K and no on all cliques of size, no on all graphs that have colorings of, K-1 colorings, and that contradicts Rasbrough's lower bound. Does that make sense?
Can I say something high level? I always found this method, just amazing, this feasible interpolation. So just to say what it does, it says that in some proof systems, if I give you a proof, we believe P is different than NP, so it must be easier to prove things than to compute them. And it seems like here you can take a proof and get an algorithm from it. So in some proof systems, this can be done, like resolution and like cutting planes. And in a sense, because it contradicts our intuition, really means that these proof systems are weak. I guess the proofs in them are, already describe an algorithm for something. At least some structural, for some structural formulas, algorithms show up automatically in any proof.
Right. Yeah. Great. Yeah, in general, the reason that we think proof systems like Frege are so powerful is that they don't have this property, that it's that you don't get, you can prove something without getting such constructive information from the proof.
I think only under assumptions, right?
I'm saying what we think. Yeah. Yeah.
If Frege had feasible interpolation, then we could factor integers with.
Yeah. So that's the original method that was used, but again, it only works for these very particularly concocted types of statements, of which random CNFs are not of that type. And then more recently, this really great result by Garg, Goose, Kamoth, and Sokolov. It's again very similar style, but it's a lifting result, but it's similar in that might not look at by the statement here, but it's similar in that it does also use a different construction in order to go from in order to reduce the cutting plane's lower bound question to a monotone circuit bound. So they prove a general result that says if you start with an unset formula F that requires large width resolution refutations, then you can concoct from F a new formula, capital F, that is going to require large size cutting planes refutation. So it's a really beautiful result. And the formula, you might be asking, well, where's the computational content in all this? It's hidden. The computational content is because the search problem associated with the formula capital F turns out has the same property, that the search problem, if you split the variables, so G here, G is a function that's you're going to compose F with this function G, the way we usually do in lifting. What that means is each original variable, let's say the original variables are Z1 through Zn, those are the variables of little f, you're going to replace that variable by a very small, so each variable Zi is going to be replaced by G applied to Xi, Yi, where these are fresh variables that are, so this whole thing is going to be plugged in anytime you see Z. And G here, you should think of this as just being a little gadget. So think of Xi and Yi as being on a small number of bits. So again, it's hidden, the computational content, but the fact is when you look at this lifted formula capital F, it's also unsatisfiable. And moreover, because we applied this inside function G to each Zi, we have effectively obtained a formula where now we have the split variables. You can think of Alice as having the X ones and Bob's having the Y ones. And so to solve the search problem for capital F, where Alice is given assignment to the X variables and Bob's given an assignment to the Y variables, and they want to find a constraint that's violated, that search problem there's a transformation that I probably won't get to today, where you can associate all the assignments to Alice with the ones of a monotone function, and all the assignments for Bob, it was zeros of the monotone function. And the communication complexity of the search problem, the original search problem, is going to be the same as the communication complexity of the Kashmir-Vigderson search problem associated with that monotone function. So so this theorem is, even though it doesn't look it from the statement, when you look inside it a little bit, it really is of the same type, where we're doing it's a fancy, very general reduction, but it's a reduction that's going to take us from, proving a cutting plane's lower bound via, going through communication complexity to eventually proving a monotone circuit lower bound for an associated monotone function. So we want to prove lower bounds for cutting planes for random formulas, and these methods won't work because neither the interpolant type formula or the lifted formulas are random. They're not random anymore. They're very structured. But still, it turns out that we can use kind of the ideas behind the proofs indirectly, because the random formulas themselves have so much nice combinatorial property and structure that if we look under the hood, look at the proof ideas, we can actually directly prove lower bound using the same tools. And it's actually there's some messiness in the proof, but the high level is really quite clean. So the statement is that random theta log n CNFs above the threshold require exponential size cutting planes refutations. So this is the one-page description of how the proof's going to go at a high level. And I can do as much details as you want. So again, we're starting with little f, which is a random formula. And I'm switching to 2n variables just for convenience, because I'm going to eventually partition the variables of f into the two halves. And it's just more convenient to think of each of Alice and Bob having n variables. So anyways, f is a order log n k CNF with 2n underlying variables, and delta is going to be sufficiently large so that we're above the threshold. And we want to randomly partitioning the 2n variables of f into two equal sized parts, x and y. Okay, and to make life easier, today I'm going to assume that I'm going to look at a different model that's not the true random model, but another random model where, let me just add a slide here. So the case today, f, x, y balanced with respect to f, you can think of this as being f is generated in this way. So f, the way you generate f is first you generate C1x up through CMX at random. So these are just random k clauses over the x variables, okay? And then I'm going to do the same thing over the y variables. So I'm just going to generate two random formulas, one over the x variables, one over the y variables, and then f is going to be and I'll just pair them up. These two clauses, I'll OR those together to get the first clause of f and so on. Okay, so this is like a cheat in a way, because now I'm guaranteed that all of the clauses are exactly balanced, and there's a way to deal with this. But for today, I'll just be talking about this case. Okay. So that's what I mean by assuming that all the clauses of f are roughly, but you can just assume that, or you can assume they're in the model that I just said, which is maybe slightly nicer to think about. Okay. Okay, so the first thing we want to do is the same way we viewed resolution refutations, is we could view them as special kinds of branching programs for solving the search problem associated with an unset formula. In the same way, we're going to do the same thing for cutting planes. So we're going to argue that you can view a cutting planes refutation as a DAG-like communication protocol for solving the search problem. And again, we'd have to take a little care that it's not just any old DAG-like communication protocol for the search problem, but it has to be one where all the paths really do like give you a certificate that the clause, that the inequality that's being violated really is violated. Okay. So we'll first have to do that, show that that a cutting plane's refutation basically can be viewed as a DAG-like communication protocol for solving a search problem, where Alice again is. So now we're looking at cutting planes refutations of F, where we're thinking of F as having these split variables, X and Y, and Alice is going to always be given an assignment to the X part, and Bob's given an assignment to the Y part. And the same search problem, they're trying to find a clause in F that's falsified by their joint assignment. Okay, so it's the same search problem, but just instead of looking at decision trees and branching programs for it, where you query variables, we're going to be looking at communication trees and communication DAGs for solving the search problem. Okay.
So this means that at every node in the DAG or decision tree, the two players will have to exchange a few bits in order to know what arrow to proceed in this DAG to.
Yeah, I'll show you that in a second. Okay, so we'll first kind of, this is known, number one is known, and it's for CP star, but you can also do a version of it without the star for arbitrary weights, and that was known. And then the second part is to show that this transformation that goes from a DAG-like communication, well, actually it just goes from the search problem, this search problem where Alice is given alpha and Bob's given beta and they're trying to falsify a clause. We want to show that search problem can be viewed, there's a very simple reduction, no communication reduction, where alpha can actually be, each of the alphas can be viewed as ones of an associated monotone function, and the betas can be associated with zeros of a monotone function. So we want to show that more or less that studying this search problem, search of F, under the split of the variables, is the same thing as studying the DAG-like communication complexity of the Karshmer-Vigderson search problem associated with the monotone function, meaning one player is given a 1 of the function, one player is given a 0 of the function, and they're trying to find a coordinate where Alice, who's given the 1 input, is 1 and Bob 0. Okay, so we want to show that basically these are the same thing. And once we have that, then we know that really we're reducing it to a monotone circuit problem. So in order to prove lower bounds on cutting planes refutations of a random F, it suffices to prove monotone circuit bounds for separating the 1s and 0s inputs of this monotone function. Does that make sense?
Yeah, I think the only confusing thing, at least to me each time I see this, is that initially the variables given to X and Y are distinct. They are, variables in X, variables in Y, but later there will be both the same set of variables, which are just inputs to this monotone function on NB, not to NB.
Yeah, so there's a reduction going on here. The alpha itself is not going to be the ones of the function, but we're going to convert alpha to an alpha prime and beta to a beta prime. And an alpha prime and beta prime are going to have slightly longer length, and all the alpha primes are going to be 1 inputs to this function here. And all the beta primes are going to be 0 inputs to this monotone function here. Yeah, so then all we have to do is prove monotone, lower bounds on the monotone circuit complexity of separating the 1s and 0s of this function. And again, the property that we'll exploit there is the same thing that we did for resolution. Really the only property we're exploiting is the nice expansion properties of the unsat formula F. Okay, so the first thing we want to do is go from cutting planes proof to a DAG-like communication protocol for solving the search problem. Okay, so this is just a way of viewing a cutting planes proof more generally as a particular type of DAG-like communication protocol for solving the search problem. So hopefully this will be easier to understand because we did it for resolution. So remember, for resolution, we had this DAG, and at the bottom it was labeled with clauses. And each of the nodes, each of the non-leaf nodes was a variable underlying the formula F was queried and associated with, so So you query at every vertex, and you also have a set of remembered, you have a partial assignment that's remembered at every vertex. In this case, we're just replacing everywhere before where you had, so you can kind of think of a conjunction of literals associated with every vertex in the case of resolution. Those were the remembered, or that conjunction is sort of the remembered assignment. This is very similar, except that now we're replacing the conjunction by a subrectangle. So remember, Alice has alpha, all possible alphas, and Bob has all possible betas. So that gives you a big 2 to the n by 2 to the n rectangle where you label all the rows with all of Alice's inputs alpha and all the columns with Bob's input beta. And every node of this DAG-like CC picture here is going to be associated with a subrectangle, R sub V. So a node V, this node is V, it's going to have an associated subrectangle RV. In the root, it's going to be associated with all the assignments. And for an intermediate, again, this is the soundness condition. For an intermediate node V with children, so if this node V has children U and U prime, then soundness says that the set of inputs associated with RV, RV, has to be contained in the union of the two below it. Okay, and that's the soundness property. And then the bottom property is sort of what's making sure that we really are getting a certificate for every time we take a, for every leaf of this DAG, you have this rectangle R sub L, and this rectangle should basically be monochromatic in the sense that all of the inputs that are in this subrectangle R sub L, all of them should, this is labeled with some particular clause, say C3 of F. So it should be the case that all of the inputs that make it to this vertex here, the clause C3 has been falsified by all these assignments. Okay. That makes sense. So I'm hoping this looks very analogous to what we did before, but we're just replacing before we had conjunction of literals, and we're replacing those by these rectangles. So I just want to show you one direction, that we only need one direction here, which is we want to see that if you have an unsat formula F and a partition of the variables of F into the two groups X and Y, if you have a small size CP refutation, then I can get a small communication DAG for the search problem. Okay, and the proof is just so here on the right is a picture of a alleged cutting plane's refutation, pi. So pi is the refutation. So at the bottom are the inequalities associated with unsat formula F. And again, each of the intermediate nodes is labeled with a line that's been derived from the two previous ones by the rule. And in this case, I don't even care about the rules as long as it's sound. So I've abstracted away the rules. This lower bound works even if the rules are other rules. And what they do is the key here is that the lines can be computed by small communication protocols as long as the weights are small. So that means the players can just like take a walk in the proof tree, always making sure that at every vertex that the line associated with every vertex on the path that they take is going to be falsified by their joint assignment alpha and beta. Okay, so at the top, alpha, every assignment starts at the top, and then what they're going to do is evaluate. So this is the empty formula, 0 bigger than 1, and then it was derived from two lines, L1 and L2. So the players will evaluate L1 on their joint inputs. Okay, and if the lines all have low weights, then Alice can just send, the line looks like, sum of AI xi plus sum of bi yi is bigger than or equal to c. So Alice can evaluate this part and send that to Bob, and then he can take that and evaluate his part and then tell Alice the answer, whether it's true or false. Okay, and the number of bits that they need to communicate is low as long as the weights are small. That's why I'm in CP star. If the weights aren't small and I'm in the general case, then I have to go to a slightly more general type of communication model where the players are allowed to, they're allowed to have calls to equality for cost 1. So it's like a communication protocol where they're allowed not just to send a bit, but they're allowed to call an oracle that computes equality or inequality at cost 1. But anyways, in the low weight case, they literally just take a path down the protocol tree. I'm assuming here that the tree that this protocol tree is, it's a little trickier than this if the proof is not balanced. But if the proof has size S and the height of the proof is like log S, then the length of the path that they'll take is like logarithmic in S, and evaluating each line, so they're going to go left. They always want to go to the side that they're falsified, right? Since you know that the top, they both are at the top by soundness, both of their joint assignment either falsifies L1 or it falsifies L2. So the point of evaluating L1 and L2 on alpha beta is to figure out which one of those two is falsified by alpha and beta. They might both be falsified, in which case they could just lexigraphically go one direction or the other. But if just one of them is falsified, they want to make sure they take the right rate path. So they take a step, and that costs them some polylog bits of communication. And if the height of the proof pi is not too big, then the total bits of communication won't be too large. Okay. And if the proof is long and skinny, then they can just do some 1/3, 2/3 argument to, like a binary search argument instead of taking a path from the top. Does that basically make sense? Is it okay? Any questions? Yeah, I'm running out of time, so I'm not sure if I should. I could cut to the end of some open problems, or I could just quickly summarize.
Maybe you can summarize what we've seen so far and what you will hopefully show us next week. Okay, great. So, so just to back up, we talked about random formulas, why they're interesting, why it's hard to certify them in any proof system, and how the Ficus conjecture that's been super fruitful to prove lots of other things. Hopefully it's true. And then we talked about actually proving lower bounds for specific proof systems for random formulas. And I showed you the old result for resolution as sort of a stepping stone to try to show the lower bound for cutting planes. And again, the idea behind all of these lower bounds is to reduce it to some kind of monotone circuit bound. This is a more complicated reduction than the previous arguments. But so far, what we did was we showed how you can view low weight cutting planes refutations. You can kind of extract from a refutation a DAG-like communication protocol for solving the search problem. And the structure of the DAG-like protocol will be very similar to the structure of the original cutting planes proof. And so the size of it, the height, everything about it will be more or less, very similar to the original one. So then it's just a matter of proving lower bounds on DAG-like protocols for solving the search problem. And the second step that we didn't do is to show, well, that's going to be the same as proving lower bound using this, using a reduction and using this beautiful result by Karshmir-Vigdersen that shows, gives an equivalence between circuit bounds and proving DAG-like bounds on, I guess this is not Karshmir-Vigdersen, but Karshmir-Vigdersen proved that for formulas or for circuit depth, there's an equivalence between proving formula size bounds and proving lower bounds on normal tree-like communication protocols for solving this Karshmir-Vigdersen search problem associated with the function. Search problem being Alice is given a 1 input, Bob's given a 0 input, and they want to find a coordinate where Alice is 1 and Bob is 0. So solving that problem with ordinary communication complexity is equivalent to formula size. And this is a generalization of that proved by Razborov, showing that you can do the same thing if you start with monotone circuits. So monotone circuits, if you have a small monotone circuit for a monotone function, that implies that there's a small DAG-like communication protocol for the monotone Karshmir-Vigdersen game for that function, and vice versa. So there's an equivalence between DAG-like communication complexity of the Karshmir-Vigdersen search problem for a monotone function and the DAG-like communication complexity of the search problem associated with our unset formula. So this is a reduction that takes us from this search problem to this other search problem. And then by Karshmir-Vigdersen, this search problem, the DAG-like communication complexity of it is the same
as proving monotone circuit bounds for this monotone function. So then the last step is just to prove monotone circuit bounds for this, and that we'll do that next time. Uses standard techniques, but it's a little bit tricky. Yeah, and I'll just wrap up with some, in case we don't finish next time, I just want to wrap up with some high-level comments. Yeah, so I think it would be really nice to get the lower bound for K constant. Again, I think this is quite related to other nice conjectures about more general and stronger sunflower lemmas, and also related to proving better lifting theorems. We also still don't know how to prove lower bounds for random formulas for bounded depth Frege, which is kind of surprising. Another question is, okay, most people, there's Ficus conjecture, we think that random CNF are hard, but as far as I know, there's really no good evidence that they're hard at all. And so one question that I would be interested in is to understand I guess it's called reverse mathematics, and reverse mathematics in general is, instead of taking like some sort of logical system and seeing what you can prove from it, you start with a statement and you want to see what's the weakest proof system that, like if you took that statement as an axiom, could you prove then everything that proof system could prove? So that's why it's called reverse mathematics, because you're starting with a theorem and you're saying how strong is it relative to induction axioms or axioms that are kind of inherent for different proof systems. So I'm asking the same question here. If you have a random, how hard is random CNF? In other words, if we added for free, and we'd have to define this, but if you added for free random unsat to bounded depth Frege, could it simulate Frege, or just give some indication that random CNF is universal in some sense? Also, there's other nice distributions that we think are hard besides random CNF, and so the main ones are if you have a pseudo-random generator, so a generator that takes a small seed and maps it to a very long string. So think of this as being like polylog n, and this is being like into the epsilon or something like that. So if the pseudo-random generator formula for this generator G would be a CNF formula that would be saying it's a distribution, because it's taking every element. So you take a particular element in the range here, so a particular assignment, to these into the epsilon variables, and you say that that's not in the range. So there's only going to be so this is supposed to be 2 to the n. I had it right before. So in other words, if you run over all seeds, there's going to be, n to the order 1 or quasi-polynomial many strings. So that means that the range of this function, the number of strings of length n to the epsilon that are going to be in the range is very small. And so almost all strings of length n to the epsilon are not going to be in the range of the generator. So the formula takes, a random one, sorry, I'm pointing there, I don't mean to, it takes a random string of length n to the epsilon and asserts that this is in the range of the generator, okay? And since almost all strings are not in the range of the generator, this is going to be unsat with high probability. So this gives us another nice distribution of hard formulas. And similarly, we can express circuit lower bound statement by taking a random formula F and having a formula that states that no circuit of size n to the 10, or there is a circuit of size n to the 10 that computes this function. Okay, so we can write that down as a formula. And again, that's a distribution because we can run over all formulas. We can run over all functions f on n variables. So these give us other hard distributions that we think are hard for any proof system. And these are even harder to prove lower bounds on. We have very little results down here. So another question is how do these relate? How do these various distributions of hard forms relate to one another? I mean, we know that these two are related, but as far as I know, we don't know anything about whether, how random CNF are relating to these. So you would think that lower bounds for these, the PRG ones, should give you lower bounds for random CNF, for example, but I don't know if much is known about that. Yeah, so that's, sorry, I'm tying it over.
Okay, okay, thanks. Tony?
Thanks.
Questions to Tony?
Hello, Tony. This is Vijay here. Thanks for a wonderful talk. You mentioned these PRG formulas, where the property of the formula is that you assert that a particular assignment is in the range, and it's unlikely to be, right? And I'm assuming that you also encode the circuit of the PRG function along with it, right?
Yeah, so you think of G as being fixed, and the way you say that something is not that something is in the range is, yeah, you run over all seeds and say that one of them gives you that value.
Okay. Thank you.
Yeah.
Yeah, maybe I have a question as well. Thanks for the talk, first of all. It was very nice. So again, to everything that relates to randomized versions of this proof. If I want to stick with, I don't know, like I think that the best algorithm for refuting a random KCNF being satisfied or not satisfied, this is actually algorithms of this type that you have a small probability of being mistaken to think that it isn't satisfiable even though it is. So are, for example, Ficus conjecture and the uses of this conjecture and things like that also work if you allow this small error of saying this is unsatisfiable even if it is.
Yeah, so are you asking whether these lower bounds would still
whether it implies anything? I don't think it.
So whether what I'm not sure. I know what.
Whether it's
said that Ficus conjecture implies other.
Oh, I see.
The condition on that. If I take a variant of this conjecture that allows a small error, does it still translate to the other?
And when you say, I think it already. So, but you mean small error on the sat ones or on the unsat? So it already is allowed to have error on the unsat ones because it only has to say unsat, say half the time.
Okay, so the answer. Yes.
And so you mean error on the sat ones?
So I think that, I mean, one of the sides of the error was probably not interesting. The side of the error was like what I had in mind is that if the formula is satisfiable, it would sometimes say that it is unsatisfiable.
I think, yeah, so I think it's okay if the algorithm is randomized in that for every SAT formula with high probability, it says SAT. I think that's okay. But what's not okay is that if it's, well, what's by not okay, I mean, I don't know how to formalize it because there's so few SAT ones where it would say SAT, where it would say SAT on half of the SAT ones, say, and something like that. I mean,
okay, yeah, thanks.
Yeah, but I think that the other kind, if it's a randomized algorithm, I think that then, yeah, it's not so much different in terms of what it implies, and also I think that you can modify these lower bounds that I'm talking about to rule that out too. To rule out randomized algorithms based on these weak proof systems of that type. Does that make sense? So in other words, these lower bounds for resolution show that, that Ficus, that there is no algorithm, resolution-based algorithm of, that runs in polynomial time or even sub-exponential time. So it kind of, it affirms the conjecture, Ficus conjecture for resolution-based algorithms. So I'm saying, I think it's that these lower bounds are robust enough to this randomized version of it. It's actually related to pseudo-determinism, but anyways, that's a different topic.
Okay, thank you.
Yeah.
Thanks, everybody.